Up to now, we have mainly talked about how we can illustrate household preferences in terms of graphs, indifference curves, and so on. And now we go more into the analytical direction, where in the end we would like to derive an optimal demand function for individuals or households. And the first ingredient that we need to be able to do that is the utility function. So essentially, utility functions are another way to represent preferences, where the utility function translates the input in terms of consumption into a number that represents the satisfaction, or sometimes called felicity, or in general terms utility, of the corresponding consumer or household. So that would be the output. Mathematically, we can write it as the function u of, say, x1, x2 to xn, where all these x1 to xn are the different consumption inputs of the individual. And all these consumption levels lead to an output of the function that we denote by u bar here, which would be the consumer satisfaction, the felicity, or the utility, or would measure it. So xi here represents the consumption of good I, and u bar the associated utility level that is determined by the functional form of the utility function. This then allows expressing the preferences mathematically, such that if the consumption bundle x1 is strictly preferred to consumption bundle x2, we would have that the output of the utility function for consumption of x1 would be greater than the output of the utility function of consumption of the bundle x2. And if the consumer is indifferent between the two bundles, then this would imply that the output of the utility function of consumption bundle 1 is the same as the output of the utility function of consumption bundle 2. So this would allow for a mathematical representation of the preference relations that we've discussed previously. Now let's illustrate this with a very simple example with two goods, where we say that x1 refers to apples and x2 to bananas, and the particular functional form of the utility function is that the utility level would be determined by consumption of x1 with an elasticity alpha, where alpha measures the extent to which more consumption of good 1 would increase utility, and consumption of good 2 with an elasticity of beta. Here we take, just for simplicity, alpha to be 1/3 and beta to be 2/3, which would basically lead to a Cobb-Douglas utility function, where the exponents add up to 1. Let's assume the starting point is a situation in which the consumer consumes 3 apples and 2 bananas and has this utility function here. Then utility would be u of 3 and 2, so we just plug in 3 instead of x1, 2 instead of x2, and what we would get is approximately 3.03 in terms of the output of the utility function. Now this consumer gets 2 more apples and 1 more banana, so the utility function would then be u of 5 and 3. So we plug in 5 for x1 and 3 for x2. And then in this case, the utility level would be 3.79. Clearly 3.79 is greater than 3.03, which is exactly what we would expect, since we have this assumption that more is better, the monotonicity of the preferences, and that's now reflected here in the utility functions, that the output of the function is greater if the input is greater. So we have that we can indeed represent these preferences here with such utility functions and compare the outcome. Then it would lead to the same comparison as if we would compare the preferences of the goods initially. It is important to mention at this point that there are two different interpretations of utility. The first one being ordinal utility, which means that we can only rank different consumption bundles with a utility function, but we cannot tell anything about how much one of the bundles is preferred to the other. So take the numerical example before with 3 apples and 2 bananas. That would lead to an output of the utility function of 3.03. With 5 apples and 3 bananas, that would be 3.79. So we clearly see that the consumption bundle with more of the two goods is preferred to the consumption bundle with less of the two goods. But the difference between these two values has no interpretation whatsoever. So according to the ordinal utility interpretation, we cannot infer from the difference between these two numerical values in any way how much the consumer prefers the consumption bundle 5.3 to the consumption bundle 3.2. Then there is the cardinal utility interpretation. In this case, one would really interpret the numerical values, the outcomes of the utility function, as utils or something like that, which would have a direct economic interpretation. So in this case, we could represent the difference in the outputs of the two utility functions here as 0.76. And in this case of a cardinal utility interpretation, the difference between the two would measure by how much the consumer prefers the consumption bundle 5.3 to the consumption bundle 3.2. So in this case, one could compare a lot of different consumption bundles, and the larger the difference is between the consumption bundles, the more the consumer would prefer the one that has the higher utility level. For an ordinal utility interpretation, we cannot do this. And perhaps it's important to say at this point that many people use this ordinal utility interpretation, and they are very cautious when it comes to cardinal utility representation, because it just would require that utility functions are indeed an accurate representation of the felicity that a person gets out of the consumption of the different bundles, and that's often seen as a too strong of an assumption. But sometimes it comes in very handy to have such a cardinal utility interpretation. Now let's illustrate utility functions with two goods. In this case, it would not be a standard function with one input and one output. Instead, we would have a three-dimensional graph here. So the utility function would be represented by a plane. Here we have x1, so the consumption of x1 on the x-axis. On the y-axis, we have consumption of good 2. And on the z-axis, we have the utility level, basically. What we observe here is that if we have little consumption of both goods x1 and x2, utility would be low. If we increase consumption of both goods, utility would be high. And if we increase only consumption of one good, then utility would increase, but at a decreasing manner. So we can hold one of the goods constant and increase the other one, then the utility function would be concave, as we will see later. To the interpretation of the utility function, I've already said that the height of the mountain is basically the value of the utility function, or if you want to interpret it as such, the number of utils. So that's here, the higher the point is on which you are, the higher is your utility level. Then we have the so-called isoquants. These are the red lines, and they represent the same utility level. So you can achieve the same utility level with more of good 2 and less of good 1, or with less of good 2 and more of good 1. So basically that's the same as the indifference curves, right? So these isoquants, along which the utility function has the same level, they are nothing else than the indifference curves. So we can infer directly the indifference curves from the utility functions. And what we have, if utility functions are concave, then the indifference curves would be convex. What does this mean? So if we hold one of the goods constant and increase consumption of the other good, then utility would increase, but at a decreasing rate. We see this here, perhaps not as well as we would see it when we plot it just in a two-dimensional case, but basically we see this. Also here along the x-line, so if we hold x1 constant and increase x2, then utility would increase, but at a diminishing rate. So that would mean that the utility function is concave in the two input arguments, and in this case, the indifference curves are then convex. We can illustrate this further. So here we have the same graph as before, but now we have another plane that intersects the utility function at a level of utility of 5. And we see here the intersection is exactly this isoquant here, or this indifference curve. So along this isoquant, you would be able to achieve a utility level of 5, or 5 utils, or whatever you would like to call it. And you can do this with little consumption of x2 and lots of consumption of x1, or little consumption of x1 but more consumption of x2, and all the combinations here along this isoquant. I said before that the utility function is concave, which means that it increases but at a diminishing rate. So that means the slope is steeper for a low level of consumption if we hold the other good constant. So let's fix x2 here and plot the utility function for the case in which x2 is 1 and we increase x1. So in this case, utility would increase with increasing x1, but at a decreasing rate. And that's exactly the illustration of what we've seen here when we just look at one side of this curve. So here will let x2 be fixed and would increase only x1. So this line here is exactly what we display in this graph, and we observe here more clearly that the utility function is concave if you leave the other good constant. Up to now, we have looked at the utility functions of standard goods with a certain degree of substitutability, but not perfect substitutes and also not perfect complements. And for the sake of completeness, we now illustrate here the case of perfect substitutes. In this case, the utility function would be linear. So it's not concave anymore. Instead, it increases linearly. The slope does not change when you have more consumption of one of the two goods. So in this case, for example, a utility function would look like that the utility of x1 and x2 is a times x1 and b times x2. So here we would see x1 and x2 don't have an exponent, or they have an exponent which is implicitly equal to 1, so it's linear. And irrespective of how much we increase x1 and x2, the additional utility that we get would not be decreasing. In this case, we plot this here for a is equal to 0.5 and b is equal to 0.3, and we would get a flat plane basically that increases with the consumption of x1 and x2, and we have perfect substitutability. So then the indifference curves would also be straight lines here, so the isoquants that lead to the same utility level, because it would just not matter whether you consume x1 or x2. The relation between the two would just be represented by the parameters a and b that represent the inherent preferences of the consumer for these two different goods. So in case of perfect substitutes, the utility function is linear and we would have a plane in the two goods case. Now we have the other polar case, the perfect complements, and in this case the utility function would have a kink. This can be represented by the utility function that we have here, where u of x1 and x2 would be the minimum of the two components a times x1 and b times x2, where it wouldn't matter again. So if you increase x2 but leaving x1 the same, then you wouldn't be able to increase utility further, and vice versa also for x1. And this would look like the graph that we have here, where we have a kink. And from here, for example, you couldn't increase utility by just raising consumption of good 2 and leaving consumption of good 1 constant. And therefore these indifference curves would be in a right angle towards each other, which we see here at this kink of the utility function for the perfect complements. To summarize and for further considerations, we now have utility functions as a very practical and common way to express preferences mathematically, and it's an important input now when we want to analyze consumer behavior mathematically. The inputs in a utility function are the consumption goods, are the different consumption bundles. Output is the utility, or sometimes called felicity or satisfaction or whatever, which you can interpret either in the ordinal way or in the cardinal way, as we've discussed previously. And if we now add the second element, the budget constraints, which we would discuss in the next chapter, then we can use the utility function together with the budget constraints to derive the optimal consumer demand functions for given preferences and given budgets. Thank you very much for watching the video, and I hope you found it interesting and useful. For more videos on economic content, please visit my channel that you find here to the left. And to the right you see the next video in the series at the top, and at the bottom you see the whole lecture in the form of a playlist.